So next, Professor Rohit Gurjar, an upcoming rock star in our department, will be joining us. So he's an assistant professor in our department. His research focuses on computational complexity, algebraic algorithms, and randomness. Today he'll be talking about QR codes and blockchain verification. Personally, I'm very interested in an example in his talk, which is about error correcting codes in QR code. So his talk will be mostly focusing on the role of algebra in computer science.
So what I wanted to talk about is showing some usefulness of algebra in computer science. I mean, you might not imagine it's much more useful than what we tend to think. So I wanted to show two examples. One is QR codes, and the other is like fast verification of computations, which is among other things which is used in blockchains. But then I realized that in just half an hour I cannot really tell you the details, and I always like to show some mathematics, so I will stick to one of the examples. So I want to talk about algebra in how it is used in QR codes. So first, what do I mean by algebra? So algebra is just basic algebra we learned in school: addition, multiplication, division, polynomials, their roots, right? Evaluating a polynomial at points and all those things. Another thing which is quite useful is modular arithmetic, which we don't really learn in school, but it's not that hard, right? I mean, so for example, if it's 3 p.m. right now, after 10 hours it will be 1 a.m., right? So how do I find this? I just take modulo 12, right? 3 plus 10 is 1 modulo 12. So that's modular arithmetic. Similarly, you do it with multiplication. So amazing thing is that everything you know with the usual addition, multiplication, that also works with modular addition and modular multiplication. So why is it useful? Why do we need it? I'll tell you. You'll realize at the end of this talk. Okay, so algebra has a wide range of applications in computer science. So for example, it's used in data compression, for any kind of communication happening from one place to another place. You can lose data, right? There could be errors. So you need some mechanism to correct errors. So it's all involves, the fundamental tool we have for handling errors comes from algebra, comes from polynomials, right? Also for cryptography, right? So reliable and secure communication. So in cryptography also a fundamental tool is algebra. This efficient verification of computation, which I talked about, which is one of the things, one of the fundamental things in blockchains. Again, it's based on polynomials. Some people are now also using algebra for software verification, right? So so algebra has lots of uses, and today I am going to show you. Okay, so before go to QR codes, let's see some quick facts, very basic facts, which I am sure you must have seen in school. So here is a basic fact from algebra. So any polynomial of degree d has at most d roots, right? Does everyone know this? Right? Everyone has seen this. So it's looks like an innocent statement, but as you'll see, it has many applications in algorithm design and in complexity theory, in general in computer science. So equivalently, you can restate this statement as, so if I give you d plus 1 points in the plane, then there is a unique degree d curve passing through them, right? So it's like saying, if I take 2 points in the plane, there is a unique line passing through 2 points, right? If I take 3 points in the plane, there is a unique degree 2 curve passing through them. Why is it equivalent? You can think about it. It's not very hard. Okay. So there is a unique line passing through 2 points. If I take 3 points, then there is a unique degree 2 curve, right? Like this. Okay. So now let me come to QR codes. and let's see why do we need at all algebra, right? So you know what, I mean, you use QR codes every day, you know why, what are the applications of QR codes, but so what is so non-trivial about it, right? I mean, so it's clearly black and white represents 0, 1. We know every information can be represented as bits, right? So you can of course convert any piece of information into 0, 1 and then black and white pixels. So what is non-trivial here? So the non-trivial part is this, that you might have observed that many times when there are obstacles, right, when some part of the code is hidden, right, or it may be even erased, still you try to scan it, it works, right? You must have experienced this before, right? So yeah, so the QR codes can be read even when they are partially occluded or erased, right? So sometimes this, I mean, part of it could be torn off, right? And sometimes what happens is it's torn off and behind it there is a older QR code somewhere, right? So what is the difference here? The difference, there is a crucial difference here, right? So the first example I showed, it was like some part of the data is deleted, right, erased. Now what is happening here? It is corrupted. Now the original, I mean the data which should have been there, now it has been replaced with something else which is wrong, right? So so this is a different challenge. So it is a harder challenge just from deletion, right? It's worse than deletion. So even this, if you scan this, even this will work, right? Even when so there are errors can I mean, this is maybe not very common example, but there are very common scenarios where errors can appear, right? So maybe, I mean, maybe there are some obstacles for due to which you read zeros as ones and ones as zeros, right? In general, in any communication channel, your messages get errors, right? So then how do you recover your original message when there are errors, right? So that's the fundamental question. So when we want to send some data, some information we want to send, and then the channel, whatever medium we are sending it through, some part of the message will eventually get corrupted, so the bits will get replaced with some wrong bits. So then how do you get the original message, right? And how efficiently you can do it? That is the main challenge. Okay, so I mean, at first you might guess that, okay, it's so I showed you that some part of it was hidden, but still we were able to read it. So it looks like maybe the same information is copied multiple times, right? So for example, let's say maybe it's like this, that the same information, we have created 4 copies and we have placed these 4 copies in these 4 blocks, right? Then, so if any one block is hidden, you can still recover the information, right? So that would be a good guess, but I mean, we can do this mechanism, but there is a problem with this. So do you see the problem? What is the problem? If you just take 4 copies, it is possible that the same bit, right, the same part of the information gets deleted from each of the 4 blocks, right? That could happen, right? Then how do you recover that, right? So we need much stronger guarantees. So I'll show you what guarantees QR codes give you, right? So for example, if you do this, so this I mean, from these 4 blocks I have deleted these 4 spots. A scanner will still be able to read this, right? Or if I do this, if I hide these parts of the QR code, you will still be able to read it. So so there are different kinds of QR codes. They have different levels of error correction. So this, what I am showing you, that is level H. So what does level H mean? Level H means you can correct even if from any part of this code, from any 30% portion of this code you can delete, or you can modify, you can replace whatever black and white pixels, you can replace them with some other black and white pixel, right? And still you will be able to read it. I mean, the scanner will be able to read it, right? So you can do this as much as 30% of this code, right? So yeah, this is another example where it works. So this will also work. This is some other less than 30% of the code which is hidden here. So someone wants to try this. Someone wants to try and scan. See what you get. Yeah, you get the RISC website, right? So it works, right? I'm not just claiming all these things. Uh, okay, now try. So that I have just enlarged the hidden part. Now it doesn't work, right? So now it has gone beyond 30%, right? So now more than 30% part is hidden. So that's why it doesn't work. Okay, so what is the magic here? So let me first let's first see what some basic facts about QR codes, right? So so there is some pixel pattern. So for example, so this it comes in many variations, right? You must have seen it. So this is a grid of 33 cross 33 pixels. So smallest is I think 21. So 21 cross 21, and then it increases with a gap of 4. So 21, 25, 29, 33, and so on. So there are 40 variations. Okay. So this is version 4. This is version 4 which I am showing you. So here 33 cross 33, that means you have 1089 total bits, right? These many pixels you have. So each pixel is 1 bit. So you have so many bits. That means roughly 136 bytes. Okay. Now all of this is not just information. So these red circles and the yellow part you see, that is some fixed pattern which we always see, which we always put, because these are used for finding the right alignment, right? Sometimes you are scanning it on a different angle, right? There are lots of variations. So we need some some bookmarks or whatever you can call it, so that you know where it is, at what orientation it is, right? So some fixed pixel patterns are there. And then also there are some pixels, I don't know if you can see, there are some green, I'm showing some green color. There's some small part of QR code which encodes format information. So format information, there are different formats of QR code. So for example, this error correction level is one of the things which is stored in the format information. Okay. So after counting all this, you have roughly 100 bytes of data. So out of 136 bytes of data, you have remaining 100 bytes of data. 100 bytes where you can actually store the whatever you want to store. Okay. So other 36 bytes go into all this fixed patterns and format information. Okay. So so we can store 100 bytes of data, and now you got this website, right? You got the RISC website. It has 29 characters. That means it has 29 bytes, right? So we are storing 29 bytes into 100 bytes of, right? We have 100 bytes of space. We are storing 29 bytes of data there. So if you use your naive idea, you could have created 3 copies, right? You could have just created 3 copies of those 29 bytes within 100 bytes. But as I told you, that will not work, because what if the same information is deleted from every 3 copies, each of the 3 copies? So what is the guarantee for level H? For level H QR code, what is the guarantee? That it will work even if you delete any 32 bytes of these 100 bytes, right? Out of these 100, you delete any 32, or even modify, not just delete, you replace them with some wrong bits. So even then you can get back the original information, right? So how do we do this, right? So this is important, right? Any 32 bytes from any part of this code, you can delete any 32 bytes and it will still work. Okay. So does this sound like a strong guarantee, right? I hope it. Do you see a solution for this? How can you build this?
Like different intensities, or let's say different information for these major 3 squares. And these 3 major squares actually tell me the crux of the QR code, where it is actually going.
It tells you the position, yeah.
Position.
Yes.
And other part is just 0 and 0. So maybe it can be possible that other part get vanished or, but that's I guess.
No, but I mean, but what we need to ensure is that any 32 bytes from here are deleted and we are still able to recover the original data.
So that is my solution, that I keep these 3 squares as more weightage intensities.
No, that squares is just for position. They don't give you anything about.
I store something on that, like more.
Oh no, that you cannot cheat. You are cheating here.
No,
You
I'm
cannot-
not cheating. I'm changing the way. I'm changing the way
No.
the
So
actual QR code is.
okay, so here is the challenge again. So you have 36 bytes of. So in fact, not just 29 bytes. You can store 36 bytes in this version of QR code. So you have 36 bytes of information. You are allowed to store it using 100 bytes, right? You can expand it. You can whatever you want to do. You can make copies of some part, whatever you want to do with that. You can go till 100 bytes. And the guarantee I need is that if I delete or modify any 32 bytes out of these 100, I should still be able to recover my original message. Okay, so this challenge is clear. At least the challenge is clear, because at the end you have to verify that we have met this, we have solved this challenge. Okay, so at the end we'll see this. So as I told you, simply duplication of data will not work. So what works is coding theory, which involves algebra and geometry, and I'll tell you the basic idea of how it works.
Maybe before you go into the solution, are there different challenges here than just regular, coding in networks and stuff like that?
No, it's just coding theories, standard coding theory.
Standard coding theory.
Yeah, I'm talking about 1960s.
Okay.
Yeah. Oh, that's what? Did you mean that?
So is that true? First of all?
I mean, of course that is true, right? Thank you. Yeah. So of course,
What did you say?
so you have to first do some image processing. You have to, you have an image, you have to get that 0, 1 pixel pattern from out of it. That is the first step, of course, right? I'm only telling you the later part of the story, right? Okay. So what is the main idea? So the main idea is that, so this is like a toy case, a simple example. So you split whatever message you have, this website, you split into 2 parts. And then so then these 2 parts, they are like 0, 1 bit strings, right? So every 0, 1 bit string, you can think of it as a number, right? You can think of it as an integer, right? So now you can, any message you can see split into 2 parts, and then you get 2 integers. So let's say that 2 integers are y0 and y1.
Sorry, are you linearizing it first in some fixed?
No, I'm just looking at the bit representation.
No, I know. You have to linearize the 2-dimensional pattern.
No, I started with the website URL.
Oh, you're coding it.
Right. So I started with the URL, website URL, and I.
Forward it.
Yeah. I mean, I have to first tell the forward direction, right? Yes. So you take the URL, website URL, split into 2 parts, right? That is what your message is. I call it message. And then, you split into 2 parts, you see 2 numbers, right? So now these 2 numbers let's plot them as 2 points on the 2D plane. So 0, y0 and 1, y1, right? I just put these 2 points on the plane. Now what do? I pass a line through these 2 points, right? Every 2 points, there is a unique line passing through them. So I take this line, and then, so remember my message is y0, y1, right? That is, my website URL is this y0, y1. Now what I'm going to do, I'm going to take maybe another 3rd point on this line. Let's say this is 2, y2, right? I just see where at x equal to 2, what is the value this line takes, right? So let's say this is y2. So then I just append this y2, I append with y0, y1, y2, right? That is now my encoding. So original message was y0, y1, and now encoding is, I just append this 3rd point y2, y0, y1, y2. And that already has the magic, right? So do you see the magic? Now, what is the magical property here? That if I delete out of these 3, y0, y1, y2, delete any one, right? If you delete any one, let's say y1 gets deleted, can you still get the line, right? You can still get the line, because, out of 3, any point is deleted, you still have 2 points, you can get the line. If you can get the line, you get the message, right? So because line is the message, basically, we are representing the message as the line. Okay, so that's the main idea. Now, but this is not the whole story, right? Because I told you it's not just deletion, right? We can also get corruption. So maybe y1 is not just deleted, but what if it gets modified, right? So now let's say y1 moves up or down. So let's say it moves down. So now it's corrupted. I don't know which 2 points are correct, right? Suppose someone gives me guarantee that at most 1 point is incorrect. So at least 2 points are correct. Yeah.
This same type of grading technique can be work or not? Normal QR code, there is only 0101.
Yeah.
But if we introduce colors for more security or
Oh,
enhanced
right.
security,
Yeah, probably, yeah.
then this technique.
Yeah, I could generalize this too. I don't know if, so Sharath can answer if you can read colors and you can get information from colors. I don't know. Yeah. Okay, so now you have these 3 points. You don't know which one is incorrect. You know 2 are correct, which you don't know which ones. So can you get the line back? I mean, the answer is no. You can't get the line because there are like these 2 also have a line, these 2 also have a line, these 2 also have a line. I don't know which line is correct, right? So deletion works, but this corruption doesn't work. So what do I do? What is the next obvious idea? One more point, right? Let's add one more point. I'm actually going to add 2 more points. So now, originally my message was y0, y1, 2 points. I added 3 more points here, right? So now I have 5 points. Now, okay, so now if you remember what was my challenge? My challenge was like roughly 30% of the data I want to corrupt, right? So 30% of these 5 points, let's say it's 2 points, okay? So let's say 2 points get corrupted. So y1 and y3, they get corrupted, so y1 moves down, y3 moves up. Now I know suppose someone guarantees that only 2 will be corrupted. So I know 3 are correct, 3 points are correct, I don't know which ones. So can you recover the line? So definitely, probabilistically, but definitely not. Why? Yeah, because there is another line, right? So there is one line is this, but there is another line which passes through 3 points, and that could be the correct line. So we don't know, right? Okay. So then next obvious thing, let's add one more point. Okay. So let's do 6 points. Okay. Now again, so my goal is 30% error, right? So out of 6, let's say 2 points are corrupted. So let's say y1 and y3 are corrupted. So y1 moves up, y1 moves down, y3 moves up. Now again, let's say someone gives the guarantee that only 2 are corrupted, so at least 4 are correct. I don't know which one. I don't know which 4 points are correct, but 4 are correct. So can you recover the line now? Yes? Why so confident? Right? So yeah, can anyone say why can we recover the line? 4 points, right? So, but I don't know which ones are correct, right? I don't know which 4 out of these 6 are correct, but the point is that y0, y2, y4, y5, they are in one line, and there is no other 4 points. There is no set of other 4 points which are in one line. So then I can uniquely determine what is the line, right? So that's why 6 points are now enough. So I started with, I converted my message into 2 points. 2 points I made converted into 6 points, and now I have the 30% guarantee, right? Any 30% of the data you can corrupt, I can recover my message. Okay, that's the main idea. But okay, so now my claim is that challenge is solved, right? We split the message into 2 blocks, right? Convert them into 6 blocks, these 6 points, right? So 2 blocks expanded, so it's like 3 times more, right? You are multiplying by 3, and now guarantees that any 2 blocks are deleted or modified, I can recover, right? So this is like the 33%, like the 30% challenge. So is this over? Is this the story over, or Am I somehow fooling you here?
So it depends on the percentage of error, right? If you increase the percentage of error, then you have to keep.
So let's say my only goal was 30% error. Yeah, so let's say, so is the 30% error challenge solved? Right, exactly, right? So these blocks, these are big blocks, right? So it could happen that one bit from each block get corrupted, right? So I have not really solved the challenge, I am just kind of fooling you here. So what I am guaranteeing that any 2 blocks I can handle, but what if one bit from each of the 6 blocks get corrupted? Then how will I recover, right? Then I have no way of recovering. So what we need to do here is we need to take small blocks, right? So if you have a big message, you split into 2 blocks, then you have really big blocks, right? And then it is possible that if you have big blocks, then it is quite possible that something from each block will get corrupted. So then I cannot do anything. So probably that I'm out of, but I started early. There was, I think I'll take till 3:30. Okay. Okay. So okay. So the challenge is solved or not solved? What do you think? Not solved, right? So we still need to do some work. So the point is that you can, instead of, I mean, you cannot have these large blocks. You should work with small blocks, right? Ideally, you should just work with maybe 1 byte. So each block should be 1 byte, right? So yeah, not really, and the challenge is not solved. So what do we do, right? So originally my message has 36 bytes, right? I was working with this example of 36 bytes. So let's say we split the message into 36 blocks. So each byte is a block. Okay, each block is 1 byte. Now I can visualize them as 36 points in the plane. So here are, let's say 36. They are not 36, but let's say there are 36 points. Now what was my trick? My trick was to pass a line through them. Can I pass a line through them? What can I pass through 36 points? Right. A curve of degree 35, right? So that's what I'll do. I'll pass a unique degree 35 curve, right? So let's say it's this curve. Then what will I do? I'll take some other points on this curve. So I'll take 64 other points. Why am I taking 64? Because I want to go to total 100. So if you remember the challenge, from 36, I wanted to go to 100.
So one
yeah?
question is, this curve is not unique, right? It depends on the order.
Oh, curve is, the degree 35 is unique, right?
I mean, so here you are visiting based on x-axis.
Oh, right. So, okay, so when I said I had 36 blocks, I had 36 numbers, y0, y1, y2, I fixed the points as 0, y0, 1, y1, 2, y2. Yeah, that is just like a canonical choice. So we don't worry about that. Yeah. Okay. So now this is what we need to show. Okay. So we have taken 64 other points. These red ones are the 64 other points. Now what you need to show, you can go home and prove this, that so if you delete out of this 100, if you delete any, not just delete, if you modify any 32 points, there is only one set of 68 points which have a degree 35 curve passing through them. Okay, it's just like the other statement I made, right? So I had 6 points, you modify 2 of them, so then there was a unique set of 4 points through which were collinear, right? That's the same statement, just the numbers are larger. So the same kind of proof maybe not the same kind of proof, but you can try. Okay, so now the challenge is solved, right? So now each block is 1 byte. So now I can say that I have 100 bytes. I had 36 bytes. I converted them into 100 bytes. You delete or modify any 32 bytes, I will be able to recover. Okay. So yeah, as I was saying, this is stuff from 1960, right? This is called Reed-Solomon code. This is one of the widely used codes everywhere in all kinds of communication. So okay, one thing I should have told you. So why do we need modular arithmetic here? Do you know? So all these polynomials, roots, evaluations, we have to do modulo some number. We can't do just over integers. You see what's the problem with integers? Sorry? Too large, right? So you have a degree 35 polynomial. If you put some integer, you'll get really large values, right? So then it will overflow 1 byte, right? It will not fit into 1 byte. So if you want to fit into 1 byte, then you should work with modular arithmetic. So you can take modulo some prime, and the magic is that it still works. So over even modulo primes, you can say that a degree d polynomial has at most d roots. This unique degree d curve passing through d plus 1 points, all of this still works over modular arithmetic. Okay. So yeah, as I was telling you, these Reed-Solomon codes and other kinds of codes, they are used in all kinds of communications. When you want to send, let's say the Mars rover wants to send data to NASA, it will use some error correcting code. Maybe it uses this one, Reed-Solomon. When you want to store huge amounts of data across, like you have many hard drives. So hard drive failure is common, right? So some part of data will be lost, so you want to recover. So there so just making multiple copies of the data is not efficient. Just like what I showed you, right? So that's not a solution. So then you need error correcting codes. Okay, so other questions people study in, so this was from 1960, but afterwards people study many kinds of questions, right? So for example, you want to do all this very fast, right? So that's obvious question in computer science. Whatever you are computing, you want to do it fast. So that's a lot of research went into that. Another challenge was like local error correction. So what I showed you, you could recover the correct point, but you have to use all the points, right? So can we correct, if some part of the message is corrupted, can we recover it just using the local information? So that is what local error correction is, right? So all kinds of nice questions are here, and people claim that these error correcting codes saves millions of dollars. Maybe it's true. I'm careful with these statements, right? So in this data storage, when people want to store huge amounts of data, they need error correcting codes, and it supposedly saves them a lot of money. Okay. So this is another part which I am not going to talk about, the efficient verification of computation. I told you so one of the crucial components of blockchains is someone does some computation and other parties need to verify that they have done what they are claiming they have done. But the challenge is that you want to verify it much faster. You don't want to don't want to do the same computation yourself, right? One way to verify is you just do the same computation yourself and then see if the answer matches. But you want to do it much faster, exponentially faster than the computation time. So verification should be exponentially faster than computation time, and that challenge is solved by polynomials and some tools from cryptography. Okay. So there are lots of applications of algebra, and some years ago I did not know this, but it seems there are many jobs. If you do specialization in algebra, in algebraic things, if you do a PhD, you will have lots of options in industry. Yeah, so that's all my messages. Okay, thanks.
So if anyone has any questions, please raise your hands.
We're talking about storing bytes of data. The way you formulated it was that the message is split into two parts, say for example, and then both the parts are encoded as a number.
Right.
And then you said the message the line between those numbers is the real message. So can you translate?
No. So that was just you can imagine that, but the real information is those two y1, y2. The points. I was just saying that you could imagine as the line is the data, because once you get the line, you can get the y0, y1.
But how do we, in our original example of the 6 points, if we have any two are corrupted,
right?
Then first of all, how do we know which two are the original ones and which are the 4 that we have just added to create the line, and how do we understand that?
So here, here my claim was that there is only one set of 4 points which pass through one line. So I can recover the line. Once you recover the line, once you know the line, then you will see what is the intercept at x equal to 0, that is y0, and see what is the intercept at x equal to 1, that is y1.
Okay.
And then you get y0 and y1.
Okay. That is the part.
That is the message, yes.
Thank you.
Yeah.
So I was asking that you had displayed the details about the website, which is of only 29 bytes, right?
Yeah.
So what if we have a data of around 100 bytes?
Then you'll use some other version of QR code, some larger version of QR code.
Okay.
Or you could compromise with the error correction level. So instead of 30%, maybe you are okay with 15% error correction.
Okay, so if we have large set of data, we have to compromise with the error.
Yeah, so either you enlarge the QR code or you compromise on error correction. Yeah, so there is this trade-off. Yeah.
So why is the 30% limit for the corruption of data? Is there any reason for that?
So the limit is actually 50%, I think. But I don't know why they stopped at 30%.
So until 50% we can corrupt the data and get the QR.
Yeah, so that is another model of error corruption. That is, you assume not, so I was assuming really worst case that any 32 can go corrupt, but you can say it happens randomly. So with some probability, some parts get corrupted. So that's another area in itself. That's like, random error correction. Security. Right. So if it has more than that 30% error, yes, it could be interpreted as a wrong. Yes. Yeah. So security part we have not seen it. Yeah.
Okay. So actually, I wanted to ask a question.
Yeah.
So basically, you said that there could be a 30% of error management.
Yes.
So, like if there is a deleted data of 30%, so it can recognize. So, is there any mechanism which can detect that 30% data is modified? Like, if the data is modified, then how will it detect the 30% is only modified? Like, it can consider that if the rest of 70% is modified, so it can consider that the 70% is correct and show the differently.
Yeah, there is no way. There's no way. If, for example, everything can get corrupted, there is no way to figure. There's no way to find out that. But like again, you are cheating.
So there is no mechanism. There is no mechanism like that for detecting that.
No.
Okay, I think we are done with the question. To thank Professor Rohit, we'll be gifting him another token of appreciation. Can we have a round of applause, please?